Hey everyone, and welcome to this explainer. Today, we're going to unpack something truly fascinating. We are diving headfirst into the invisible, dynamic world of changing states of matter. But we're not just stopping at the theory. Oh no, we're going to pair all that physics with the precise, rigorous lab techniques you actually need to measure these changes. I mean, it's one thing to just know that water boils, right? But it's an entirely different skill to measure that process like a true scientist. So let's jump right in.
Check out this incredibly crisp, high-definition image of a boiling kettle. It's a super familiar sight to almost all of us, right? But I want to use this everyday scenario to bridge the gap between our normal routines and these strict scientific measurements we're about to learn. Inside that metal kettle, a profound physical transformation is literally happening right before our eyes, driven entirely by heat. To really understand it, and more importantly, to measure it without making crucial errors, we've got to transition our mindset. We need to go from being casual observers waiting for a cup of tea to focused scientists gathering precise data.
So, here is our roadmap for today. First up, the dance of changing states. Second, measuring volume with precision. Third, tracking temperature accurately. Fourth, setting up the experiment. And finally, we'll wrap up with data and lab safety. Let's go.
Section 1. Changing states and the dance of matter.
Okay, let's trace the complete cycle of water, starting over with solid ice. If you just leave ice sitting out in a warm place, it follows that melting path to become liquid water. Heat that liquid water up enough and it boils, right? It turns into steam, which is an invisible gas. But the really cool part is that this whole dance goes backwards too. If that steam touches a cold surface, it condenses right back into a liquid. And if you put that liquid in the freezer, well, it freezes back into solid ice. It's just a continuous, beautiful cycle of physical change.
But as scientists, we can't just casually say, oh, it gets hot and changes. No way. We need absolute precision. And that brings us to our key definitions, melting point and boiling point. These aren't just vague ideas. They are highly specific, measurable thresholds. The melting point is the exact temperature where a solid becomes a liquid. The boiling point? That's the exact temperature where the liquid rapidly changes into a gas. For water, that boiling point is exactly 100 degrees Celsius. When we run our lab experiments, this is the exact number we are hunting for.
Now notice the sharp contrast between two processes that honestly confuse people all the time: evaporation and condensation. Evaporation happens gradually. Think of a puddle on the ground slowly disappearing into the air as it changes into invisible water vapor. The warmer the day, the faster it happens. Condensation is the exact opposite. That's when that invisible water vapor touches something cold and, seemingly magically, reappears as liquid water droplets. Getting this difference locked down is absolutely key.
Section 2. Measuring volume with absolute precision.
All right, I'm going to let you in on a little secret that completely separates amateur measurements from professional science. When you pour a liquid into a measuring cylinder, it does not sit perfectly flat. It actually forms a little curve at the top. We call this curve the meniscus. To get an accurate measurement, you literally have to follow these 3 steps perfectly. 1. Locate that meniscus. 2. Get your eye perfectly level with it. And 3. This is crucial. Always read the volume from the absolute bottom of that curve.
Just look at the eye placement here. See how that dotted line goes straight from the eye to the very bottom of the curve? If you're standing up looking down or sitting low looking up, the lines on the cylinder are going to misalign with the liquid, and your data is going to be completely faulty. Getting your eye on that exact level is the secret sauce to true accuracy.
Section 3. Tracking temperature accurately. Think about how a thermometer actually works. Inside that glass tube is a liquid that physically expands as it gets hotter, forcing it to rise up the scale. It's pure physics. But, a tool's only as good as the person using it. Look at the practical application here. A thermometer suspended in a beaker of water that's being heated. Notice how it's held perfectly in place? It's not just casually tossed in there, it's positioned with total, deliberate intent.
And that brings us to the strict accuracy rules for tracking temperature. First, just like with volume, your eye must be level with the top of the liquid inside the thermometer scale. Second, the bulb at the bottom needs to be fully submerged in the water. But here is the ultimate lab secret that ruins so many beginner experiments. The bulb must not touch the bottom of the beaker. Why? Because the glass bottom is sitting directly over the flame. If your thermometer rests on the bottom, you're measuring the scorching hot glass, not the water. Total rookie mistake that will completely ruin your readings.
Section 4. Setting up the experiment. Let's look at this brilliantly assembled lab setup.
It's a thing of beauty, really. At the base, we've got the Bunsen burner bringing the heat. Above that, a tripod and a heat-proof mat supporting our beaker of water. But the real star of the show here is that clamp stand holding the thermometer. By using the clamp stand, we perfectly suspend the thermometer so the bulb is deep in the water but safely hovering above the glass bottom. It hits all of our accuracy rules in one brilliant mechanical setup.
So with the equipment all assembled, here's how we actually run the investigation. Step 1. Accurately measure 150 cubic centimeters of water into your beaker. And yes, remember to read the bottom of that meniscus. Step 2. Secure your thermometer with a clamp stand so it's hovering above the bottom. Step 3. Get that water heating. And Step 4. Measure the temperature every single minute until the water is vigorously boiling.
Section 5. Data and Lab Safety.
Look, to capture reliable data, you have got to be highly organized. This table layout, this is exactly what you should draw in your notebook before you even think about turning on the Bunsen burner. Notice the consistent 1-minute intervals: 0, 1, 2, 3, 4. By using a stopwatch and recording the temperature at these exact set intervals, you're creating a perfectly consistent, trackable data set. You're not just guessing, you are meticulously logging reality. And once you've got that table filled out, the next step is graphing. Taking those raw numbers and plotting them helps us instantly visualize what's going on. You'll plot your time in minutes right along the horizontal axis, and your temperature measurements up the vertical axis. Suddenly, a boring list of numbers transforms into this visual slope, showing you exactly how quickly the temperature spiked, minute by minute, as it raced toward that 100-degree boiling point.
Okay, let's pivot to absolutely the most important topic of all: safety. Protecting your eyes and your body is the single most critical step of any lab work, period. The 2 golden rules are: always wear safety spectacles to protect your eyes from sudden splashes, even if they aren't the most fashionable accessory. And, interestingly enough, always stand up to carry out practical work.
Now, that second rule kind of catches people off guard. Why do you think that is? Why is it a strict, non-negotiable rule to stand up during a heating experiment instead of just pulling up a stool and sitting comfortably at the lab bench? Think about the physics of the setup we just built, full of boiling 100-degree water.
While the answer is ingeniously simple and literally potentially life-saving, standing prevents accidental hot spills from landing directly in your lap. If you're sitting and a beaker of near-boiling water shatters or tips over, gravity does its thing. That scalding liquid pours straight into your lap and you are trapped by the desk. But if you're standing, you can instantly take a step back and the liquid spills harmlessly onto the floor. It is a super simple posture change that serves as an absolutely brilliant safety solution.
All right, let's look at this summary checklist to recap what we've conquered today. We can confidently check off that we know the 3 states of matter. We know how to use terms like melting, boiling, and condensation to describe how water shifts around. We've totally mastered the insider rules for using a thermometer and a measuring cylinder, reading that meniscus, and keeping the bulb off the hot glass. And finally, we know how to carry out an investigation safely, standing up with our safety specs firmly on.
As we wrap up, I want to leave you with one final thought. The next time you see a steaming cup of coffee, a frosty window, or even just a kettle boiling in your own kitchen, ask yourself, what invisible data points am I missing here? What is the exact temperature threshold being crossed? Where exactly is that invisible water vapor going? Try to look at your everyday world with the sharp, measuring eye of a scientist. Thanks so much for learning with me today, and keep exploring the fascinating physics all around you.